Hi guys, in this video I'm going to be showing you how I used depth first search logic to modularize a parser to whatever grammar you want. So I have this set up to take in the grammar as an input file. So here's the grammar that started it all. Back in the summer I took this course at Ohio State, CSE 3341 with Timothy Carpenter. It's called Principles of Programming Languages. And in this course, over the semester, we were tasked with writing a compiler. And this is the language definition we were given. It's right here. I added this lower part for clarity because I wanted everything to be strings instead of Java literal strings or literal integers. I didn't want any of that. But this part was given to us. And we were tasked with first writing a scanner. A scanner just means getting basically like the words or technically the tokens of the language. So get the procedure, A is begin, integer, X, semicolon, end. And then from there, we want to parse, which means make a parse tree. If it's a tree, it's going to be recursive, which is shown in the grammar here. We have these, we want to start with a procedure, but then we're going to have an ID. So we need to go over to the ID. So you right there, and then you basically figure out which one of these it's going to be. I'm not going to go and explain all the grammatical rules, but know that it is recursive. And when I looked at this, like the natural idea is to make a method for each one of these and say, okay, I'll make a procedure parse method, and that'll call the ID parse method, and the declarative sequence method, and the statement sequence method. Or if you find this other case, it will call these other ones. Well, it's not that much different here, but you get the point. It's just identify what your non-terminal is, identify which one of these choices is going to be, which is separated by these OR symbols. And then if it's a terminal, that's not too hard to parse through. If it's a non-terminal, you just recursively call the next method. And I thought, you know, a lot of that decision making is very generic. There's not really much to do as a human, you know? You look at expression, it's term plus expression or it's term minus expression, and I mean the plus or the minus, who cares what the meaning of it is? It's so simple in the parsing logic. Why can't this be automated? So that's what I attempted to do. I don't have this grammar hard-coded into this program. I'm going to put it in right now and run it. The test file, what is that? It's test course. I run that. I want the parse tree of this expression right here. And there it is. And these question marks are supposed to be bullet points. Here I've created a really simple grammar for the purpose of demonstrating how the decision making works, how the depth first search logic gets executed here. So if I take this grammar and I just generate the grammar, this is what it's going to look like. We have a decision tree right here, and in this decision tree we start with empty and we also end with empty. So every string from the root to a leaf node is a sequence that the non-terminal can take on. So it can go ABC, or it can go AB and then empty, or just A empty, and then XY or YX, or hold on, I'm missing one. It would be the X empty, and then also just empty. We go empty to empty. So we use empty to denote the end, or the start or the end of a sequence. And so we also have a parse tree for X. So we have not a parse tree, another decision tree for X. So we have a decision tree for every possible, what you call it, non-terminal. So now I'm going to demonstrate what happens if we run our demo grammar on our demo test cases. So I put this in here. After we have the grammar shown here, I'm going to see the parse trees for each one. So we have the empty case that just starts with the starting terminal and then goes to empty. And then if it's A, B, right there, A, it's just going to see A. And then if it's AB, ABC, if it's X, it's going to detect that the X non-terminal works. XY, same thing, and then YX, of course, if you see a Y non-terminal before, that's going to take you to the Y path. And that is every case within this because there are no cycles, so it's a finite grammar. So what if we tested this on an infinite grammar instead of a finite grammar? Here I have a very simple cycle where your only non-terminal can call either nothing or an element plus itself, plus the non-terminal, go back into the non-terminal state and detect for another X again. So if we run this, we'll find empty case works, single X works, two X's works, and a lot of X's works. And so this very simple and easy grammar with the X in front works because you can always just check, does it start with an X or is it empty? The problem here is cycles. If we put the S before the X, then we get the classic recursive descent parsing problem, which is infinite recursion. You get a stack overflow, so I'll show that right here. Or even, no, I guess I still need that. So let's run this. Stack overflow. For the rest of this video, I'm just going to show you some of my cooler test cases. This first one, even AB, is just the language of strings consisting of A's and B's in which there are an even number of A's and B's. This next one, arithmetic, it's very simple. This is kind of the de facto standard when you're talking about parsing. It's a very simple thing to understand with its correspondence with the order of operations. And then finally, I'll show you the magnum opus, big guy.